solve this, we'll use a unit circle containing two triangles. On the bigger triangle, B can be found by using the trigonomic definition of tangent of theta equals opposite over adjacent. We know the adjacent is equal to 1 because the radius on the unit circle at any given time is 1. And our unknown opposite is going to equal B. So what we're saying here, since tangent of theta equals opposite over adjacent, tangent of theta also equals B over 1, which is the same as saying tangent of theta equals B. So our B side is tangent of theta.
Next, we need to find the height of the smaller triangle. Since we know that any given point on the unit circle is given as cosine theta sine theta, we also know that the height is given as the y of the point on the unit circle. So the height equals sine theta.
Now we need to find the area. For the triangle's area is given as 1/2 base times height. On the larger triangle, our base equals 1 and our height equals tan theta. So area equals tan theta over 2. On the small triangle, our base equals 1 and our height equals sine theta. Our area equals sine theta over 2. The area for a sector is given as 1/2 theta radius squared. As we remember, the radius of a unit circle equals 1, so our area ends up equaling theta over 2.
So, the small triangle is equal to or less than the sector, which is less than or equal to the large triangle. Now we multiply by 2 over sine theta. The sine thetas will cancel, as will the 2's, leaving us with 1. And the 2's will cancel, leaving us with theta over sine theta. On this one, tangent theta is also equal to sine theta over cosine theta. So the sine thetas will cancel, as do the 2's, leaving us with 1 over cosine theta. We take the inverses. Since we are finding the limit as theta approaches 0, and we also know that cosine theta when theta equals 0 is 1, we can replace the cosine theta with 1. And here we find that the limit as theta approaches 0 is sine theta over theta. The sine theta over theta must equal 1, because it cannot be greater than or less than 1.
Alright, so what would you say your favorite part of this project was, or what you enjoyed most?
I think what I really enjoyed was coming together and working on the Squeeze Theorem. I feel like it squeezed us together, and we really bonded.
Well, definitely just working with a bunch of kids who understand math the same way that I do, and just being able to share our math abilities together is just a great part of this project.
I guess what I really enjoyed was being able to work with people who not only understood the math, but like actually working with people who had done this sort of problem before, because like, as an actor, sometimes it's kind of hard to get into character, but when you're around the exact type of people who know what it is you're working with, it really helps you get into the zone.
And what was your least favorite thing, or something you had problems with?
We had trouble getting together, and also the idea that there's so much math out there that we don't even know. And it's just so hard knowing that we can't share all our math knowledge with everyone. And that was definitely a big minus.
It was kind of difficult to coordinate times and getting everyone together at once.
Yeah, just, putting a close to this chapter. It was hard.
I guess originally I did have a lot of issues getting into character. Like, I don't know, it was just sometimes I couldn't really think, like, what would this type of person do at this point? How would they say this? But I mean, luckily there was a point where it finally clicked for me that, like, wow, we're actually doing here what mathematicians all over the world end up doing at some point. And I guess that really helped me actually find myself.
Finally, what do you hope this project that you've worked on will accomplish?
Most definitely world peace.
World peace. Yeah, world peace.
Well, In truth, I really hope this video will be a wake-up call to Congress. Being shut down right now helps no one. We need to find a resolution now and solve all of our problems.